So exam 2 is graded. I've handed it back to all of the folks here. I think there are 3 total off-campus exams that I picked up this morning that people did a little later. So those are not graded yet, but I think those are the only 3. But so the plan for today then will be to take a look at those exams and walk through the solutions to it. The scores were generally pretty good. Then we'll take a look at some of the average power stuff, complex power stuff, and then there's a quiz on average power kinds of things. And so just as a little bit of fair warning, we'll look at this average power stuff again real quick so that you can, if you have any questions, you could ask them, or otherwise just kind of pay attention to this part because that's the key thing. Yeah, I don't have a whole lot else in the way of announcements. As far as I know, I don't have anything to hand back to you in terms of grades, so that's a plus for me. Yeah?
Once we have that homework done by?
Shoot for something like probably Monday. If you're ready for Monday, if for some reason I chose to push it off to Tuesday, you'd be okay. But shoot for Monday, I think. The most of the problems are fairly straightforward, but it does cover some material that we won't necessarily finish until today, maybe tomorrow. So, but then you should have plenty of time to work on it. Do a couple problems each day, you'll be set. So, all right. Exam statistics are on the page or on the screen behind me. The average, at least in class, was a nice evil value of 66.6 points, which is about 83%. So it's not a terribly high average, but it's also not low. I think it's a pretty fair average given the exam that as I wrote it. It felt like it was a little on the easy side. It focused more on core concepts than most other exams, so that's, I think, an appropriate number. The median was 70.5 points, or about 88%, so half of you got an A or better, or a B minus, or an A minus at the worst kind of thing. The maximum, a couple of people got exactly 1 point off, and then the standard deviation, or the average distance from the average, was almost 15 points, which is pretty big. And I think, to be fair, that has to do with, I think, pretty much just one really weird score that really pushed that one off. But so that is the exam's statistics. Take a look at the problems and walk through the solutions. So let's move this out of the way for a minute. All right, so that was the exam statistics. Problem 1 had the dependent source in it, asked you to do a Thevenin analysis on it. And to be honest, I stole this one directly from the book, or at least the old version of the textbook, because I didn't feel like writing one. So the voltage that we're looking for is across this resistor here, which is a 3K resistor. This is a 2K resistor. This voltage source gives out VA over 2, where VA is the voltage across this 1K resistor up here. And then this is a 6-volt source. The problem asks you to do a Thevenin analysis, or specifically it says to use Thevenin's theorem to solve it. Most people did that, but there were a few people, it was a little disappointing that they showed some odd work that didn't really go anywhere and then wrote 2 1/4 at the end, just after using like mesh or nodal analysis to solve for it. And like, come on, I can tell when I look at the number, but then I can go back up and see that you didn't actually do any Thevenin analysis. But because this has dependent sources in it, we need to do both we need to find the open circuit voltage as well as the short circuit current to figure out what's going on in terms of that Thevenin analysis. And there weren't any particular surprises here, I don't think. It's all very straightforward. So we pull out that resistor, and for our VOC solution, we have a pretty straightforward circuit. Basically, there's just one loop. I think the only major problem that I saw people have here was, what is the polarity on this VA over 2 voltage? When they were essentially writing the KVL around the loop to solve for the value of the voltage. So if we do this properly, we should get negative VOC minus VA over 2 plus V2K equals 0. So the open circuit voltage equals, say, V2K minus VA over 2. So that's probably the key place people, if they messed up at all, that's where they messed up. You just have the one loop coming around here. There's 3 kiloohms of total resistance, 6 volts, and so you have a 2 milliamp current rolling around. What that means is that the V2K is the 2 milliamps times the 2 kiloohms, or 4 volts, and VA is 2 milliamps times 1 kiloohm, or 2 volts. So we plug those things in up here. We've got 4 minus 2 over 2 is 1, and that's 3. So our open circuit voltage is 3 volts. When we solve for the short circuit current, this one is fairly straightforward. Not a lot of kind of, I think the only weird thing about solving for the short circuit current is that you end up with if you do it as a mesh analysis, one of your coefficients is not a whole number. It's a 1.5. But so the circuit solving for the short circuit current, same thing here. I'm not going to write in all of the circuit's values, but we're solving for the short circuit current here, 2K. I wrote my loops going around like this, I1 and I2, so I2 is the same as the short circuit current. When you do that, the first equation works out, we have negative 6 plus 1K times I1 plus 2K I1 minus I2 equals 0. Simplify that down to 3K times I1 minus 2K times I2 equals 0. So that's the first one. The second one, you have 2K times I2 minus I1 plus VA over 2 equals 0. We need to know what VA is. VA is 1 kiloohm times I1. So you can stick that in there, and that makes that, essentially that makes that 0.5 kiloohms times I1. And so when you simplify all this stuff, what you should have is negative 1.5K times I1 plus 2K times I2 equals 0. Whoops, this should be 6 up here. That 6 moves on to the other side. So here's your second equation. When you solve those simultaneously, you get that I1 is 4 milliamps for what it's worth. Not like it matters a ton. But I2, the one that we care about, which is the same as our short circuit current, is 3 milliamps. Which is pretty convenient since the Thevenin resistance will be the open circuit voltage divided by the short circuit current. So we have 3 volts divided by 3 milliamps, which means the Thevenin resistance is exactly 1 kiloohm. So, just to kind of squeeze the last part in on this sheet of paper, what that means is we've got our Thevenin equivalent for the circuit. We've got a 1K resistor up here and a 3 volt source. This is our open circuit voltage. This is our Thevenin resistance. And in the first place, we had a 3K resistor hooked up here, and we want to know what the voltage is across it, V0. And so V0 is going to be some fraction of the 3 volts with 3K on top and 3K plus 1K on the bottom, which equals 2.25 volts total. So I guess the key quantities to make sure that you'd been able to properly solve for: what is our Thevenin, what is the open circuit voltage, what is the short circuit current. Those are the key things that I was concerned with. And making sure that you did the solution properly. There are at least 2 or 3 people that still tried to do they tried to zero out the sources to solve for the Thevenin resistance. You can't do that when you have dependent sources, so don't do it. So that was the first question. People did mostly well on that one. I'm not going to write down specifically the answer for the second one. The idea, I had a hard time phrasing the question to make sure that I wasn't just kind of saying, look, tell me the answer that I want to hear. But the idea was, I don't remember what it specifically asked. Specifically says, when we solve first order transient circuits, we see 2 interesting behaviors from storage elements like inductors and capacitors that allow us to analyze the circuit without using differential equations. Describe the behavior exhibited by either capacitors or inductors and explain why both behaviors are valid. So one thing is that you guys still can't really read instructions very well because I got a lot of answers that describe something about one thing about inductors and one thing about capacitors, and like, just pick one of them. Last semester in 3173, I actually got tired of people not reading the instructions, and so on the front page of the instructions, I put on the last bullet says, if you've read this far, write your name on the second page of the exam backwards for like 2 extra points. And of like 25 students, no, 40 students, I think 8 did it or something like that. It was really depressing. But anyways, you're supposed to choose either inductors or capacitors, and basically what I was trying to get you to say was that instead of having to deal with the differential equations on the inductors and capacitors, because of the way that they behave, because the current through an inductor can't change instantaneously, or because the voltage across a capacitor can't change instantaneously, when that switch flips, they essentially act like a current source if it's an inductor or a voltage source if it's a capacitor. That's one part of what I was looking for. The other part was this idea that under steady state conditions, an inductor acts as a short circuit and a capacitor acts as an open circuit. And that has to do just with the nature of the way, if you look at either the impedance equations, the J omega L or the 1 over J, or negative J upon omega C, either way you look at that, that will give you an explanation as to exactly why the behavior occurs. But those were the things that I was looking at. If you gave me 1, I gave you 3 points, as long as you came close to answering the question, more or less. So, yeah, that was what I was looking for. Steady state behavior, that it goes to either a short circuit or an open, or just after it switches, it acts like a source. And so we can analyze it using our other methodologies, or Thevenins, or nodals, or mesh, or whatever. So that's what I was looking for that one. The third question was pretty straightforward. I was trying to get something that would be as simple as possible while still getting you, basically what I wanted to see for question 3 was, do you understand the process? And I saw that people, for the most part, did understand the process. You may see a lot of scribbling on the score for this one. I had to go through and do it twice because I realized about halfway through, or maybe 3/4 of the way through grading the exam, that I had made a mistake in my solution, which was just the sign on one of the terms. So I had to go back and fix that. But the question, we have a current source, a 16K resistor, the switch in this position initially, and over here is a 20 kilo ohm resistor, which made the answer fairly large in terms of, I guess, voltages. And what we were solving for was the voltage across this this resistor over time, with a 10 Henry inductor here and a 16 kilo ohm resistor here. Not like it matters at all. I mean, at all. So you can pretty much ignore the fact that that resistor has any, it doesn't affect the analysis in any way. This is a 10 milliamp source, which combined with the 20 kilo ohms makes for some fairly large numbers. But the first thing that we're supposed to look at is what does the circuit look like at time 0 minus, or just before the switch is actuated, and what it's doing is it's moving to the other position at time t equals 0. So basically you just have a current source, you have this random resistor, and you have a short circuit, and we want to solve for what is IL. We have 16 kilo ohms of resistance for what it's worth, we have 10 milliamps of current, and what we're solving for is what is the current through the inductor at time 0 minus. Well, it's 10 milliamps. I mean, there's not really any analysis to be done there. It's pretty much done for you. So I sub L of 0 minus is just 10 milliamps. But it's important to note which direction that current is going. That's where I messed up when I did this, because I was going a little too fast. So at time equals 0 plus, you have a current source like this with a magnitude of 10 milliamps. And so the rest of the circuit is like this. We've defined V0 like that, and so when you multiply this together, you can think about it however you want, but in order to kind of satisfy things, you can say that the current is actually negative 10 milliamps times the 20 kilo ohms, which gives us negative 200 volts as the first, and that's V0 of 0 plus. So that's the first part. Next part is looking at the circuit at time greater than 5 tau. And there's nothing happening in this circuit at time greater than 5 tau. There are no sources, so there's nothing to drive this voltage, and therefore it's just 0. So there's nothing happening there. When we look at what is the Thevenin resistance for this circuit, as seen from the storage capacitor, or from the storage element, it's just, well, it's the 20 kilo ohms, because that's all that's still part of the circuit. Not much else to say there. So our Thevenin is the 20 kilo ohms, and that makes our time constant tau, which is L over our Thevenin, which was 10 divided by 20,000, which is 1 over 2,000, or it's like 0.0005, I think. So when we solve for our constants K1 and K2, K1 just equals 0, K2 equals a negative 200 minus 0, or just negative 200. And so you plug all of that in, and V0 as a function of time equals negative 200 e to the negative. And what I did is I pulled the 2000 up, 2000 t, or negative 200 e to the negative t over 0.0005, either or. And most people did a good job with that one. I don't remember seeing much more than math errors in that one, for the most part. Question 4 was, this one went pretty well too. I think, again, primarily what we saw were math errors. I don't know that anybody got part 1 wrong or part A wrong. Just asked, given the circuit components, is it underdamped or is it overdamped? and we can solve very quickly. We have alpha is 1 over 2 RC. Omega naught is 1 over the square root of LC. Start plugging in numbers. We have 1 over 2 times 1,000 times 10, which is a fairly small number. So alpha itself equals 5 times 10 to the negative fifth. Whereas the numbers for this were somewhat more well chosen. You have a tenth times 10, which means that will equal 1. Square root of 1 is 1. 1 over 1 is 1. And so omega naught equals 1. Because omega naught is greater than alpha, that means that the circuit is underdamped. And I think most people got that. I don't remember seeing a single wrong answer on that one. Part B was a little bit more, really all I saw wrong here were math errors. People generally did a good job with this one. If the circuit is going to be critically damped, and the reason that I put hopefully in the problem statement was that idea that we're dealing with real circuit elements that have tolerances, and getting a critically damped circuit is pretty hard to do. But if that's the case, then alpha equals omega naught. And I think strictly speaking, alpha squared equals omega naught squared, but if you take the square root of those, alpha equals omega naught. And boil all that down, and what you should see is that the square root of LC equals 2RC. Square both sides, so LC equals 2RC squared. Divide both sides by C. And so L just equals 2RC squared over C. When you plug in all of those numbers, so that's going to be 2 times 100 times 1 times 10 to the negative third squared divided by 0.1 times 10 to the negative third gives you 4. So I think one of the only problems that I remember seeing with that, and I saw it a couple of times, where a lot of people kind of assumed or forgot somehow that we primarily talk about capacitances on the order of microfarads, and a lot of people worked with microfarad numbers instead of millifarad numbers. But that was the only problem that I saw in that one. So. Next one didn't go too bad either. The only thing that became difficult for me in doing the solution for this problem was the different ways that people dealt with their impedances, whether they expressed them in polar form or in phasor form, or if they expressed them in rectangular form, and to exactly what degree they you took out your decimal points. But most people did a good job with this one. You can look at your exam for the original problem statement, but when you convert all of these to impedances, with the radiant frequency being approximately 628 radians per second, that's the number that I used. You may have used something with some more decimal points, but that's the one that I used. You should end up with negative J 9.1, J 188.4. This stays 12. There's a resistor here too. That's 12. This should be negative J 7.96. This is 12, and this is J 125.6. So that was one of the key things. Could you get the right impedance numbers? And again, people took these out to slightly different decimal point ranges and whatnots, and so your answer might be just a little different than this one. But when I did the solution, I didn't redraw the circuit a ton of times, but created an equivalent impedance Z1, which is the the J188.4 in parallel with the negative J9.1. And when you do that, you should get a negative J9.56 or thereabouts. Z2 was the two 12 ohm resistors plus the parallel impedance Z1, which just gives you 24 minus J9.56. Then I turn my attention to the other side of the circuit for an impedance Z3, which is just the sum of the 12, the J125.6, and the negative J7.96, which should give you 12 plus 100, J117.64. And then those last two numbers, the final equivalent impedance is going to be equal to Z2 in parallel with Z3, and that should give you 26.48 minus J4.25. So again, the only thing that you would see that I saw in there were I think it must have boiled down primarily to, did you plug things into your calculator right, and did you calculate the original impedances? I think people in general they recognize, you guys understand the parallel and serial, what's in parallel with what, and so that I don't worry about at all. So this last question actually was a little weird. When I went to solve it, I hadn't. If you do it as a mesh analysis, it's actually quite easy, and you don't even have any of the complex impedances don't show up. All you have are the real impedances, the resistances that show up. And solving this one as a mesh or as a nodal analysis is quite difficult, and I only tried it once, but I couldn't get it to work. So I tried it as a superposition, and I got the same answer. And I'm like, okay, good. I'm convinced that this is the right answer. But when I first plugged it into my calculator, it was throwing me errors about singular math when you try to include all of the equations, and it's kind of nasty. But it's actually a fairly straightforward question as long as you recognize that, for instance, the top loop has absolutely nothing to do with the rest of the circuit, at least in terms of what we're solving for. So what we want to see specifically is there's a 10 ohm resistor here, 10 ohm resistor here. We want to solve for the current I0 that's flowing through the right-hand 10 resistor, 10 ohm resistor. I have a source 12 at angle 0, another one at angle 0 amps, that's volts. This is negative J10, and this is positive J10. And that actually runs you into some fairly major problems if you start analyzing that, because the impedances from those two resistors cancels each other out. And so essentially you have from an equivalence impedance point of view, you have a short circuit up here, which throws things off in terms of the analysis if you try to go too deep with it, which is kind of a problem. But if you do this as a mesh analysis, which was the point when I designed the problem, I did these in terms of I1 and I2 like that. So what that means is that I2 just equals a negative 1 at angle 0 amps. And the final solution, I0, is going to be equal to I1 minus I2, which is realistically I1 plus 1 at an angle of 0 degrees. And there are a few people that forgot that I1 or I2 was defined as going in the other direction. And so, you got a slightly wrong numeric answer, even though everything else was solid. So we can effectively ignore the top loop. We write the equations around just this pane right here. So you get positive 12 at an angle of 0 plus 10 times I1 minus I2 plus 10 times I2 equals 0. Say 20 I2 is what you have total. Sorry, 20 I1. I changed you have 20 I1 minus 10 times I2 equals a negative 12 at an angle of 0 degrees. Substitute in this fact and you get that 20 I2 equals, so you end up with minus 10 at an angle of 0 degrees. You add, or actually, since this was a negative and this was a negative, you get plus 10 at an angle of 0 degrees. You subtract that from both sides, and so you get negative 22 at an angle of 0 degrees. Divide that by 20. I2 is a negative 1.1 at an angle of 0 degrees amps. So plug all of this back up into here. You've got negative 1.1 at an angle 0 plus 1 at an angle of 0 gives us negative 0.1 at an angle of 0 as our current. So given that all of the sources were at 0 degrees and you were working wholly with real impedances, you could have done the problem without doing any kind of like AC analysis. You could have thrown away all of the angles and all that stuff and gotten the same answer. But so that was the exam. If you have any questions or concerns about the way that I graded it, why you got points off on a specific question, if I added up the numbers wrong, any of that kind of stuff, please let me know. I'd like to fix that. Scores are posted, all that kind of good stuff. So let's take a look at some of the stuff before we do the quiz. I want to remind you specifically about average power because that is the topic of the quiz. That is, so listen. It always it almost bugs me a little bit when I know that I don't always announce and say, this is the topic that I'm going to quiz you on. But in classes, I will even make a point of giving out the answers to the quiz during the class prior to the quiz, and people will still kind of miss it. And I'm just, I probably wouldn't listen to me either, so whatever. So let's look at the slides for a minute. Average power, just as a reminder, we skipped out on the calculus of necessarily deriving this, but what we're trying to do is we're taking the instantaneous power over a certain time period, and when you do that, it gets rid of, for the most part, it gets rid of the all of the sinusoidal stuff and gives us a number that we can hold on to. And it's just calculated as V sub m times I sub m, magnitude of the voltage times the magnitude of the current, divided by 2 times the cosine of what we know is the power factor angle, or the difference between the phase angle of the voltage and the current. For purely resistive circuit elements, because the voltage and the current are in phase, the cosine term just goes away, and because it goes to 1 specifically. And so the power is just 1/2 times the voltage times the current. And for purely reactive circuits, or purely reactive circuit elements, the cosine term of 90 degrees, which is the difference, drives the average power to 0. So what you need to be able to do on the quiz is the same kind of stuff that we did during our examples of this, which is given a voltage and a current and whatnot, be able to figure out what the voltage and current are going through a specific circuit element, and then use the 1/2 Vm Im times the cosine of theta b minus theta I to calculate what the voltage or what the power actually is. Yeah, so that's that's what you need to be able to do for the quiz. Hopefully you can look back at your notes and feel comfortable with what exactly we're going to do there. So the average power that would be absorbed or produced by a reactive circuit element like an inductor or capacitor will be 0. There won't be anything, but that still changes the phase angles of the voltage and the current enough so that, or the relationship between those phase angles, so that you can't just say, well, it's 1/2 Vm Im for all of the resistors in the circuit. But then we talked again yesterday about RMS values, root mean squared. So you should be somewhat comfortable with this. Again, the way that we'll do that, you'll take the function, you'll square it, you'll take the integral over a finite period of time, and then divide by that period, that same amount of time, then take the square root of that answer. Excuse me. For our purposes, we're just going to multiply the peak value, or we're going to divide the peak value by the square root of 2 to get the RMS value. Or if you have the RMS value, you multiply by the square root of 2 to get to the peak value. We did at least one example of that, which I'll never ask you to do again. We talked extensively yesterday about the power factor, which is the cosine term in our average power definition. It's this bit right here. It's called the power factor. Very important to us in terms of figuring out what's going on. And we saw yesterday how a bad power factor can cause, I guess, you to buy more electricity or buy more power from the power station than you necessarily need. Yeah, so we talked about that. And we started looking at some of the practical things about power factor angles. Purely resistive loads have a unity power factor of 1. Purely reactive loads have a power factor of 0. We have to specify whether the power factor is leading or lagging. Our capacitive loads will create a leading power factor. Inductive loads will create a lagging power factor. And as I said yesterday, primarily what you see are lagging power factors in industrial loads, at least. Today, what we should be able to get through is how to correct bad power factors. Now that we understand that bad power factors cost us money. So we did a couple of quick examples. And this is what most of the problems look like when you're doing power factor things. Just here's some information. It consumes a certain amount of power. It's got a specific power factor. It's taking in a certain amount of voltage. What is the current that's running through there? How do you quantify the amount of power that's being sent by the substation or whatever? And then I had you guys do another example of figuring out how does it change when you change the power factor. Then one of the newer things that we got into is this idea of complex power, which allows us to represent both the apparent power, the real power, and the reactive power. And the most important thing when you're calculating this complex power is to remember to take the complex conjugate of the current. Don't forget this little star. It's very important. If you forget it, most of your numbers will be pretty close, but your phase angle will be wrong. So don't forget that as you're doing all of these calculations. So when you kind of break that down, what you see is that you can multiply the RMS voltage times the RMS current, and that's going to be at the power factor angle. And you can use all of that stuff in some way to solve what you're looking for. Yeah, we used both of these to some extent to find like the real power is just the RMS current times the RMS voltage times the power factor itself. You can remember that the cosine there that is the power factor, And then finding out what the imaginary power or the complex power is, or the reactive power, you do the sine instead of the cosine. Again, as I mentioned yesterday, I changed this on these slides, but complex power in total, when you say that S equals some number of, you've solved for something, say 25,000, the units on S are always going to be voltamps, not watts. But the components, for example, this P part is measured in watts, and the Q part is measured in voltamps reactive, or just, I will always pronounce it as VAR. I don't know if that's an industry standard or not, but I like to pronounce them. So just for what it's worth, when you're dealing with those. Resistors, they absorb real power. They have no complex component to them at all. Inductors have no real component. They only absorb reactive power. And capacitors, fortunately for us, generate reactive power, which is pretty cool because we can use capacitors generally to to supply the reactive needs of our inductors. And that's going to be the whole basis of power factor correction, is putting capacitors in parallel with the rest of our load in order to kind of provide reactive power for the inductors. We looked at the power triangle. I will draw this one again just so you're feeling comfortable with it, but you have on some sort of axis, if this is the, let's see, this was going to be the real axis, this will be the imaginary axis, and in a I guess a simple way, you can have your complex power S is composed of the real power P and the reactive power Q. And being able to relate to any of these things, because it is just a right triangle, this is the power factor angle, is the angle at which S is rising up. And any of the normal sine, cosine, and tangent calculations all hold because it's a right triangle. So for example, if you want to know what the power factor angle is and its relationship to P and Q, the tangent of the power factor angle theta is going to be Q over P. And that's opposite over adjacent, SOHCAHTOA, all that kind of jazz. And so then we came up with some amount of a process to try to solve for S if you have one of them. And we did okay getting through all of that stuff. So one of the things to be aware of is that you should rely most heavily on I squared R for determining the complex power, because if you have any complex or reactive impedance in your imaginary impedance in your circuit, the V squared over R doesn't hold. So we did one example. We got at least one more that I want to do, and it's very similar in flavor to the first one that we did yesterday. So do I have this one written out? Yeah. So this is the basic setup. I'm going to copy this stuff down onto the paper so that we can work with it later. But we know that the real power consumed by this particular load is 40 kilowatts. And we know that the power factor is 0.84 lagging. We know that the voltage across the load, call it V load, and that's a phasor, is 220 volts at an angle of 0 RMS. We know that the impedance in the line is 0.1 plus J 0.25 ohms. And we want to find, in our laundry list of things, the power lost in the line. So we'll call it P loss, not P loss, but S loss. What's lost in the line, the complex power there. And then what is the total complex power that's required to be generated by the source. So the first thing that we need to do is find out what is the complex power of the load. What we have is the real power of the load, and we want to find out exactly what is the power of, what is the complex power that the load is generating. So the load's complex power, at least the magnitude of the complex power, is going to be 40 kilowatts divided by 0.84. And that's just trigonometry. We're taking, this is the cosine, and then you've got, see, that's adjacent over hypotenuse. And so we just rearrange the terms of the cosine function to find out what the load is, or at least the magnitude of the load. So 40 divided by 0.84 should give you about 47,619. And then we can do an inverse cosine to find out what is the angle theta, the inverse cosine of the power factor angle itself, or of the power factor to 0.84. Second, 0.84 gives us 32.86. So one way of quantifying the load or the power in the load would be 47,619 at an angle of 32.86 degrees. As much as anything, just for a sanity check, we like to think about the complex power in rectangular form so that we can separate out the real power from the reactive power. And so we can say, well, 47,619 at the angle of 32.86 degrees. That gives us a rectangular version of that of about 40,000 plus J. Just to keep it about at the same precision, say 25,838. Put in units here. And our sanity check, real quick, hey, we got that P is 40,000. That's what it better be, because that's what the problem statement told us it was. So you can very quickly see when you've made a mistake there, I suppose. So that's the load, and now we're going to use our normal complex power thing that says that the complex power is equal to the RMS voltage times the complex conjugate of the RMS current. Rearrange terms, find out what the current actually is. That's going to be I conjugate equals the voltage, the power divided by the voltage. So that is 47,619 at an angle of 32.86 divided by 220 at an angle of 0. And that gets us, we'd like to see that as a current, or as a phasor. And so we get 216.45 at an angle of 32.86 degrees. But you remember, this is the complex conjugate of I. This is not I. This is the complex conjugate of I. And so when we want to know and we start using in the future what is the current, the RMS current I, it's 216.45 at an angle of negative 32.86 degrees. And that's amps RMS for what it's worth. Okay, so why did we do that? Well, we need to find out what the complex, now we finally have the values that we need to solve for S loss, what is lost in the line. So we'll take the impedance in the line, we'll multiply that by the magnitude of this RMS current squared, and that will get us the losses in the line. So our RMS current, or at least the magnitude of the RMS current, is 216.45. The complex power in the line will be 216.45 squared times the line impedance, which was 0.1 plus J 0.25, which means the complex power in the line was, let's see, multiply 216.45 squared times 0.1 plus J 0.25. Put that as a phasor, and you should get 12,000. Well, my number looks, oh, we don't want it as a, well, here it is as a phasor if you care. 12,614.9 at an angle of 68.2 degrees, but we're more interested as a in rectangular form, which is about 4685 plus J 11712. And actually it's a little closer. If we do good rounding, it should be 713. So the total losses, or the total what is being generated by the source, will be what is consumed by the load plus what is lost in the line. The load we calculated to be 40,000 plus J 25,838. The losses we just calculated to be 4685 plus J 11,713, which gives us a total of 44,685 plus J 37,550 volt amps. And just so that it's clear from yesterday, the part that I kind of blanked out at the end, if we wanted to know what is the voltage that's going to be needed at the source in order to supply this load, we can just do a simple KVL and say what is the voltage at the load plus what is the voltage lost in the line. We calculated, we know what is at the load. It was given to us in the problem statement, but we need to calculate what was lost in the line by multiplying our RMS current times the load, which was 0.1 plus J 0.25. And so that was, the full thing was 216.45 at an angle of negative 32.86. Multiply that by 0.1 plus J 0.25. Sorry, I'm kind of squeezing that in there. 216.45 at an angle of negative 32.86 times 0.1 plus J 0.25. Look at that as a phasor. You should get 58.28 at an angle of 35.33 degrees. 58.28 and an angle of 35.33 degrees. So the total voltage required at the source plus 220, 269.66 volts at an angle of 7.18 degrees. So you could also calculate like the power factor at the input or at the source. That'll be the power factor there, call it power factor source, is the cosine of theta v, 7.18, minus the power factor, or the angle of the current, which was a negative 32.86, so 7.18 plus 32.86. So you get a power factor of about 0.77, lagging, just for what it's worth. But that's kind of going beyond what the problem asked us to solve for. In this case, we could have stopped here and said, we found the power that was required by the source, we found the losses in the line, we did that up here. So those are the two answers. This is just kind of going beyond where we went yesterday, or beyond where we needed to go, and just kind of reinforcing the stuff from yesterday. So what we'll do, we'll try to give you 20 minutes for the quiz here, just so you have plenty of time to work on it. We'll finish this up on, I guess tomorrow is Thursday, so we will finish up and we'll do power factor correction tomorrow. And I guess we'll start looking at some resonant circuit stuff, which means that I gotta look at that myself and refresh my memory on that stuff. Is there any questions? Average power, complex power? Okay. We'll do this quiz and we'll see you tomorrow.